Hey YouTube, welcome back to my data structures in TypeScript series. In this video, we're going to go over the implementation for the indexed D heap, not the binary heap, which I'll get into in a bit. And the indexed D heap is the implementation for the indexed priority queue abstract data type. So let's hop into this. We have a class called min-indexed D heap, which takes in a generic type T. And our first private variable is going to be the degree D of every node in the heap. So this is a generalization of the binary heap. Instead of every node having at most 2 children, in this version of the heap, D heap, it can have up to D children. So we can set D equals to 2, 3, 4, 5, and then our nodes will have a maximum of that number of children. The reason why we want to generalize, the reason why it's helpful to have a generalization of the binary heap in the form of a D heap is because sometimes a degree of that's higher than 2 can be more efficient. It's more efficient because you're having more children, your tree will be shorter in height, and that means the swim operation has less levels to go through. It's not so log base d of n. So log base d of n is less than log base 2 of n when d is greater than 2, right? So that means when the swim operation, if we have many swim operations, which is common in decreased key, then having a degree higher than 2 is going to be faster because we have less levels to swim up through. So when we decrease the key, we have to swim up in a min heap, right? But the caveat with this is that because we now have D children, when we are swimming down, we have to do D comparisons because we have to swap with the smallest or greatest child depending if it's a min or max heap to maintain the heap invariant. So if you have a lot of sinking, then a degree D of higher than 2 is not the best case. So just something to note, if you're a bit confused, then look into it yourself of why D heaps, the use case of D heaps and why they're better than binary heaps in some cases. And that's with decreased key, and decreased key are prevalent in algorithms like Dijkstra's and Prim's minimum spanning tree. And if you're a little bit confused with that, it's okay. You can still get by with the tutorial, the video lecture, and just pretend that this is 2 or something. But I suggest for you to look into why having a degree higher than 2 can be beneficial at sometimes. The next instance variable is our private instance variable size, which is just the size of the heap. We cannot use the length of the raw heap array anymore, and we'll go into that later. Next, we have 3 arrays. The first 2 arrays are the first 2 arrays that I introduced firstly in the previous video of the introduction. We have our heap, which is just a list of our keys, and you can think of this as mapping positions in the heap to key indices. If that's confusing, just think of it as keys. We then have our position map, which maps the key indices to positions, but now we only have keys and we want values. So we have our value lookup, which is an array of type T generic or null. We then have another instance variable, which is the compare instance variable, and this is a compare function that clients must provide if the generic type T is not some sort of primitive. And then in our constructor, we take a required parameter, which is the degree, because we need to set the degree, and an optional parameter, which is compare function, if, of course, the generic type T is not primitive, and we can't use the default equals. So then we set the degree to be the maximum of 2 or degree. We need the degree to be 2 because we need the tree to be complete. We can't have it be a linked list, or then SinkSwim will be bounded by linear O of n, not O of log n, so we need it at least to be 2. So we take the maximum of the degree in 2. We set the size to 0. We set all of our 3 arrays to be, just construct them to be empty arrays. And then we set the compare function, the compare instance variable, to the compare function if it exists. Otherwise, we're going to use the default compare, which is just using the comparisons. So the first 2 methods are the inspection methods. I've renamed this section from niceties to inspection because we're inspecting the data structure. And the first method is the size. This is as usual now. We return this dot size. We're not going to return this dot heap dot length, and that's because we can't use the length of the heap anymore. We will get into this later. So this returns the size of the heap in constant time and returns a number. The next method is empty. Returns a Boolean, true if the heap is empty, false otherwise. This is just going to leverage this dot size. we're going to return this dot size is equal to 0. If it is, then it's going to return true and false otherwise. So the next method is the single method for the insertion section, and this adds a value with an index to the heap. And this adds a value with an index, this should really be key, to the heap while maintaining the heap invariant in log d n time. So this is really just log n time. So here we take two parameters, a key and value, no longer just a value because now we have keys in our heap. And this returns true if the insertion was successful and false otherwise. So the first line is we need to check if the key exists. If it exists, we can't insert it because our keys have to be unique values. So we're going to implement this method later, which is the contains, but we're going to call if this dot contains and pass in the key. If this is true, then we're going to return false because we don't want to insert a key that has already been inserted into our data structure. Otherwise, the key doesn't exist, so we're free to insert it. The first thing I'm going to do is insert the key into our value lookup. So this dot values at the key is equal to the value. So we have our key value lookup. Now we have to worry about adding the key to our heap and the position of the key in the position map. So as usual, let's push the key to the end of our tree to maintain the structure variant. So this dot heap dot push key. And then we're going to increment the size instance variable, which keeps track of the size of the heap. Next, we're going to get the key position and put that in the position map lookup. So for clean code, I'm going to say create a constant key position equals this dot size minus 1, which is the last element. And then we say this dot position map at the key is equal to the key position. So if you remember, the position map is a mapping from keys to their positions. So then when we need to do stuff like removing specific elements or checking to see if keys have some sort of index in our binary heap, we just have to reference this position map, which is constant time access. Finally, we're going to try to swim the key up because we're potentially violating the heap invariant, which is for this min heap, every value has to be smaller than all of its children. So we're going to call this dot swim, and then we're going to pass in the index, which is the key position. And that's it. So swimming will take care of doing all the swapping in the heap and doing all the swapping in the position map. All we're doing is just, like, the only thing that's different between this add method in the index priority queue and the regular priority queue is that we are on top of pushing some sort of value onto our heap. It's now a key, and we now have to insert the value in the key value lookup and the position in the key position lookup. The next method peeks at the topmost element in the heap in constant time access because that's the root, and returns type T or null. Going to add that. So what this does is if the heap is empty, we're going to return null because there is nothing to peek at. Let's return null. Otherwise, we're going to return the value of the first element in our heap. So, but now our heap no longer stores values, it stores keys. So we're going to get key is equal to this dot heap at 0. And now that we have our key, let's unlock the box and get the value with our values lookup. So let's say const value is this dot values indexed by the key index, and then we're going to return our value. So this next method, value of, returns the value of the key provided if it exists. So it's going to have a return type of T or null. So we're going to first check to see if the key is, we're going to check to see if the data structure contains the key. If it doesn't, we're going to return null. So we'll do that by if this contains the key, if this does not contain the key, return null. Otherwise, we can get the value by unlocking the box with the key provided by the client. So const value equals this dot values indexed by the key, and let's return the value. So the next three methods are updating. We have update key, decrease key, and increase key. Update key is a more general version of decrease and increase. You can do whatever you want, and decrease and increase are strictly what they say they are in the method names. So update key takes two parameters, a key, which is a number, and a value, which is the gerund type T, and it updates this key to be value. So the first thing we have to do is check to see if the key exists, and if it doesn't, we're going to return false, because we can't update a key that does not exist. So we're going to say if this does not contain the key, then let us return false. We're going to also do another check to see if the value is null, because our original value lookup is an array of type T or null, and values get set to null when the keys get deleted. So if they want to update a key that's been deleted, then we won't let them. Technically this should not happen, but I think I have to do this for TypeScript. So we check to see if this dot values at the key is falsy, and if it is, we're going to return false because that means it's null. Otherwise the key exists, so let's first update this in the key value lookup. So this dot values at the key is equal to the new value. But now we're potentially violating our heap invariant, so we have to try to heapify it. So let's grab the position of the key and then sink and swim the key. So we're going to say this const position is equal to this dot PM, and then we're going to index into the key, and then we're going to call this dot sink at the position and this dot swim at the position. And this is going to try sinking it first and then swimming it first second if necessary. So before, we would have to update the key, we would have to do a linear search to find where the specific key / value is in our heap array. But now we have constant time access, so this method is O of log n, and really base d to the n, because sinking and swimming are log n time. The next two methods are more strict versions of update key. If you're calling decrease key and the value you provided actually increases the key, it's not going to let you do it. And likewise for increase key. So again, if the data structure does not contain the key, we're going to return false. Otherwise, we also need to check to see if the value is falsy, if it's null. And we need to capture it because we need to compare it later. So we're going to say const old value is equal to this dot values indexed into the key. If old value, so this is where we're repeating this line up here from update key, if old value is null, then we return false as well. So if this was the same thing as update key, if it had the same behavior, we're going to update the key and then potentially sink or swim the position. And right here I have new value. But now we want to check to make sure that new value is indeed less than our old value. So we have a helper here that we're going to implement later. If this less for values, and we're going to check if new value is less than old value, then we can update the value. And then this can run no matter what, because if we don't update the value, then sinking and swimming won't do anything because it's already in a good position. The heap invariant is not. The heap invariant will have already been held since we don't do any updating. And then increase key is the same as decrease key, except that the check is different. It makes sure that the old value is less than the new value. So new value has to be greater than the old value. And decrease and increase key run in log n time as well. So the next method is searching, and this is contains, and it returns true if this key is in the binary heap and false otherwise. This is really easy now that we have our position map. We don't have to do a linear search on our heap array. All we're going to do is make sure the key, the value of the element at the index key in our position map, that's a mouthful, we're going to make sure that it is not undefined and it's not -1. And the reason why it's potentially -1 is because we set positions to -1 when they get deleted. So here we're going to return this dot position map at the key does not equal undefined. So this is just making sure it doesn't exist. And if it does exist, make sure it's a positive position. It's not some sort of negative position that we're going to set later on. And we have to make sure that the position of the key does not equal -1. And this runs in constant time, not linear anymore. So the next three methods are deletion methods. And the first one is pull, which removes and then returns the topmost element of the heap in logarithmic time, and this returns T or null depending if it's empty. So if this heap is empty, we're going to return null. Otherwise, we're going to return the element at the root. But our heap array only holds keys. So to return the value of it, we're going to have to look up the value in the key value lookup. So we'll put this in a variable, in a constant, key to be removed is equal to this dot heap at 0. And this is the only way we can access this element representation is with the heap, because the heap is the raw ordering of the tree. It's our complete binary tree. And then we need to now remove the key. We need to first, let's not remove the key, get the value of the key. So we say value is equal to this dot values at key to be removed. We didn't want to return the value for the client, but then now, let's make sure this variable name is correct. But now we want to actually remove the key, the whole entire value at that position. We want to remove the entire root. Because we have some sort of complex representation of the root, we have 3 arrays we have to deal with. We're going to abstract that away into a method call, and we're going to call delete key with our key to be removed. And we'll implement that next. So actually, the delete key returns the value of the key deleted, so we don't even have to do this. We can just return the value that this dot delete key returns. Great. So delete key deletes the key, and it returns the value of the key. First thing we do is check if the heap does not contain the key, then we're going to return null. And then the steps for the delete key look like this. First, we're going to save the value of the key so we can return it later. The next thing we're going to do is, if you remember from the previous 2 sets of videos of the regular binary tree, we swap the root with the last element to maintain our order invariant. We then want to swap the node that's about to be deleted with the last element to maintain the order invariant of our complete binary tree. So swap root with key, it's a bit confusing, with the last node in the tree. Then pop off the root, which is now the last node of the tree because of the swap. And then we want to heapify, which just means we want to heapify the heap, which just means try sinking and swimming to make sure that the newly replaced element in our removed position is not violating the heap invariant. The position from the position map, because we no longer have a position for the key. And here we want to save the value of the key so we can return it later and then delete it as well. So those are the steps for our delete key method, and let's go through them. So we're going to grab the value by using this dot values into our key. And then it's possibly null. So I'm thinking this is for Typescript compiler errors. I do not know how this could happen, but if the value is potentially null, we're going to throw a new error. That means it's already been deleted somehow, and then we're calling again. Otherwise, we're going to delete it, so we're going to set this dot values at the key is equal to null. So that deletes the key value recording of this key. We then want to swap the node with the key, with the last node, because this is not the root. This is deleting a specific key. It could be the root, but it's not necessarily the root. So we're going to say const removed element position is equal to this dot position map at the key, right? And then we're going to say the last element position. So I should call these nodes, not elements. They are elements technically, and they are technically nodes. Last node position is equal to this dot size minus 1. We then swap the removed node position with the last node position. After we swap it, the removed node position is going to be at the end of our heap. So we're going to just call it this dot heap dot pop, and then we're going to decrement our size. Now the last node is going to be where the removed node was because we swapped it. So when we call sink and swim, we have to call it on this position right here. So first, let's try sink, and then swim. Finally, we remove the position from the position map. So we set this dot PM at the key is equal to -1, and then finally return the value for the client. And that was delete key, which runs in logarithmic time because sink and swim are the main methods that dominate the runtime of the method. The last method of the set of deletion methods is clear, and this clears the heap in constant time. So this dot values dot length is equal to 0. the position map, delete everything. The heap itself, delete everything, and then set the size back to 0, and that's clear. So I have two helpers that I've already included the implementations for. This is GetChildrenPositions and GetParentPosition. So for GetChildrenPositions, this takes a parent index, which is a number, and it returns an array of numbers, which is the array of children positions. So it's going to first create the indices array and return this, and then the main loop of the method starts at 1, and it goes all the way up until the degree d. And then it pushes to this indices array the formula for the index of the child. So it's parent index times 1 plus 2 plus 3 plus 4 whatever plus I. The next method is just the reverse. From a child index, I want the index of the parent, and this is just going to be the floor of the child index subtracted by 1 divided by the degree. The next two methods are methods that check to see if the first parameter is less than the second parameter, but we have two different use cases that we'll see in the bottom three methods. What less for positions does is check to see if the value at position A is less than the value at position B, and then less for values takes raw values, and we use both of these in the last three methods. So less for values is the easier one to implement. We just call this .compare, which is the comparison function on A and B, and check to see if that is less than 0. If we're given positions, we have to find the keys at those positions, and then for those keys, find the values. So we have to traverse kind of two lookups. So key A is equal to this.keys, sorry, not this.keys, this.position map is equal to this.heap at position A, and const key B is equal to this.heap at position B. Great, we have keys, but we want to have values. So value A is equal to this.values at key A, and likewise for B. And now we can call compare because we have the values. Value A, value B. You'll notice that our type error is that argument of type T or null is not assignable to type T, and this is because value A and B are potentially null. So if value A is equal to null or value B is equal to null, then we return false. Then we're going to throw a new error, which is values or utils.values does not exist error. And the reason why value A and value B are potentially null is because the values array is an array of type T or null, and we set values to null when we delete it. So that is the two helper methods that we're going to use in the bottom three methods. We have sync, swim, and swap. Let us implement swim first, which is the easier of the two. This swims an element with the index k, which is a number, until the heap invariant is satisfied. And this runs in log and time because we have a complete binary tree. In the worst case, we swim the entire element or node up the entire tree. And this does not return anything, it just swims it up if possible. So we first get the parent position with this .get parent position, and we pass in the index for what we want to get the parent position for. And then we loop as long as the index is positive, so we're not, like floating above our root, we're not outside of our array. And the values at these positions are, the value at the parent position, or the value at the position k is less than the value at the parent position. And that's why we need this less method for positions in particular. So we pass in k and parent position. So we want to do the swapping if our current node is less than our parent node, because this is a min heap. Every node has to be less than or equal to all of its children. So then here we have to do the swapping. We're going to call swap, and swap takes the positions k and parent position. We will then point k up, we're going to move the pointer k up to point at where the node is now, which is now at the parent position. And then we're going to recalculate parent position, which is this dot get parent position for k. And this loop will continue to bubble up, swim up the nodes until the heap invariant is satisfied again. So sync is the sync method. It syncs the element with index k until the heap invariant is satisfied. This runs in d log n time now, because In the worst case, we sink the element down the entire height of the tree, and at each level we have to do D comparisons to find the smallest child to swim down. So D, of course, is a constant with big O gets removed, but it's still it's still important to remember that it's there, because if it's a binary heap, if D is equal to 2, then 2 log n is 2 log n. But if our D is like 10, then that constant still has a significant portion to the runtime, right? Because we have to check 10 children to find the smallest child, and we swap that child when we sink down. And remember that we have to find the minimum child, because when we do the swapping, that maintains the heap invariant. If we swap with a child that's not the smallest, then other children will be smaller than the new promoted child. So we first have a loop, which is just a while loop, and we're just going to have a constant Boolean expression true. We're going to get the children positions. So all of the children positions for the node at the index k, get children positions. We then want to get the position of the smallest child. So smallest child position is equal to, we're going to assume it's the first one, not this dot. We're going to do children positions. We're going to assume it's the first one. And then we will get back to that later. Let's now assume that we have the smallest child position. If the child position is out of bounds, and this is the potential for the child position to be out of bounds because we're dealing with an array, we're not just following pointers, or the element is less than the child, so that means we have to stop sinking down because the heap invariant is satisfied. If these two variables are true, then we break. The way we construct this Boolean expression is to check to see if the smallest child position is greater than or equal to this dot size. And the way we get the element is less than child is use the less method for positions. So element is less than child is equal to this dot less for positions, and we pass in k and the smallest child position. So if either two of those are true, then we break. We'll get back to this in a bit. Then we do the same thing as the swim, where we swap the smallest child position with k, and then we now move the k pointer down because we just swapped it. And then this will loop back up and recompute the child positions for the new k. So to get the smallest child position, going back to this, we're going to have a loop, and we're going to say for every child position, const, for every child position of the smallest child, or no, not that, of the children positions, we're going to check to see if the current child position is less than the smallest child position we've seen so far. So let's first build up our if statement. If the child position that we are currently accessing is in bounds, and the current child is smaller than the minimum, then we're going to update the smallest child position to equal the child position that we're at right now. And let's construct these Boolean expressions. And again, I'm just doing this for readability's sake, so you guys know I don't have to explain it with comments. The child position is in bounds if this is opposite of this gets flipped. And the current child is smaller than the min if this call is true, less for positions. We pass in the child position and then the smallest child position, right? Because we check to see if the value at this position is smaller than this position, and then if it is, then the current child is indeed smaller than the minimum. So that was the sync method. We're going to keep looping. We're going to grab the children positions, and then this itself takes O of D time. This is the O of D at each level. We have to loop through each child, which is D because degree D, and then we make sure it is not out of bounds and make sure that the current element is not less than the child. If it is, then we have to stop looping because we're good. The heap invariant is satisfied again. Make sure that doesn't happen. If it does, then we break out because we're done syncing. Otherwise, we swap the values at the current positions k and smallest child position. I think I'm just going to move this here. And then we move the k pointer down to repeat the loop. And this is going to take log n time because this loop potentially runs log n times because the tree is log n. And because the O of d is inside the log of n, the total work is d log n. So this goes to show that for bigger values of d, your sync starts to suffer because you have to do more comparisons for your children. So really, a greater value of d is beneficial if you're doing a lot of swimming because that decreases the height of the tree because log d is less than log base 2. Log d of n is less than log base 2 of n because d is greater than 2. The last method is swapping, and we have to swap the values at the positions. But now we no longer just have to swap the raw values in the heap. We have to swap the positions marked in the position map as well. So first, let's get the keys. Let's get key I is equal to this dot position map, this dot heap at position I. And the same thing can be said for j. The key j is at the jth position, jth index in the heap array. And then now we swap the positions. So we say this dot position map at key I is equal to position j. So key I is being moved to position j. And key j is being moved to position I. So we're moving the positions that we're marking down. And then now we swap the actual keys. So the key at position I is going to be key j. And the heap at position j is going to be equal to key I. So swap first swaps the positions in our position map and then swaps the real keys in our heap. And we don't swap our values because the keys still map to the same values. We're just swapping the nodes. We're swapping the nodes of where they sit relative in our binary tree data structure. So that was it. That was the minimum indexed D heap, which is a generalization of the minimum indexed binary heap, which is the implementation for the indexed priority queue. So I hope you enjoyed that. One thing you'll notice though is that these operations are the best time operations we can get with binary heaps. In the next few videos, we're going to introduce a few heaps called binomial heaps and Fibonacci heaps that make these operations a lot faster. I'm talking about constant time access. So I hope you enjoyed, and I'll see you in the next video. See you then.